Well, good morning, everybody. Welcome to the session number 1 of our symposium on metal organic frameworks, the Argentina Symposium. En castellano, bienvenidos a todos los panoparlantes a la primera sesión de nuestro simposio, continuando con la apertura que hicimos la semana pasada con el profesor Jean Ma. Hoy vamos a tener una sesión de 3 charlas plenarias y después vamos a tener una sesión de flash y finalmente por la tarde vamos a recibir a la profesora Horcajada para otra sesión de perspectivas. Bueno, gracias a todos por estar y de vuelta los invitamos a hacer sus comentarios tanto en inglés como en castellano en nuestro chat o en la transmisión de YouTube, que ya debería estar empezando, y nosotros le vamos a transmitir a todos los panelistas sus preguntas y en caso de que no sea posible hacerlas en vivo por cuestiones de tiempo, lo vamos a hacer por privado, vamos a enviarles el contacto para que esas preguntas lleguen a los panelistas. Again, in English, welcome again, and thanks for attending to this first session. This morning, we are starting our program with Min2. I'll introduce Min2 in English so he can also understand what I'm saying, and I'm not saying anything wrong. So Min2 received his Bachelor in Science in Beijing Mining Technology University, 2008. Then he received a Master Science in Chemical Engineering in Dalian University Technology in 2011. Then he moved to Bochum in Germany to receive his PhD in organic chemistry in 2015. And since then, he has worked in 2 different groups in Germany, so as postdocs in Professor Rob Amelot's group in Leuven University with a Marie Curie fellowship. Then he moved to Max Planck Institute for Kohlenforschung in Mulheim, Newman Lab. So he has quite a lot of experience in many different topics related to porous materials, catalysis, and also research interests are based in electron beam lithography of MOF films, also chemical vapor deposition approach for MOF synthesis, MOF films, and lately also confinement of luminescent gas molecules in porous host materials. He is now working as a group leader in the Shanghai Institute of Microsystems and Information Technology, CIMIT, which is affiliated to Chinese Academy of Science. So it is our pleasure to welcome Min in our symposium. So I see now Min is sharing screen. I think everything works properly, I guess. So please proceed, and the screen is yours, Min. Welcome.
Thank you, Marius. Thank you for your kind introduction, and thank you for your kind invitation to give me this opportunity to present my work, which was done during my PhD and mostly postdoc in the KU Leuven in Belgium, in the group of Professor Amelot. And good morning, everyone. And I'm gonna start. So everything fine, Marius? Okay, great. So I'm gonna go ahead with my work. So today I'm gonna talk about a topic. I'm gonna talk about my recent work on the surface engineering of nanoporous metal organic frameworks. Okay. Yeah, so we all know that MOFs are like porous crystalline materials. So it has very high porosity and it has uniform pore size distribution. So apart from the application in something like bulk applications like gas storage, catalysis, or gas separation, some kind of this kind of these bulk applications, they also has bright future in optoelectronics or electronics based on fascinating, it's interesting properties. For instance, these host-guest interactions, we can probably use in chemical sensors. For instance, we can have guest molecules being absorbed in the molecules. Then we can induce some physical signal changes that can be transduced to some chemical sensors for chemical sensing, or some electrical conductivity can be also for some electrical applications, and also some luminescent MOFs. It has the future for example, light emitting diode, or also luminescent chemical sensing. And also we know most of the MOFs are insulator, so it gives this. It has a very low dielectrical very low dielectrical constant, so it can be used in dielectrical layer. So based on these very interesting properties, so we think MOFs can be used in these electronic devices. So to integrate these kind of materials into microelectronics, so we need microfabrication rods to integrate these kind of materials into the devices. So we can look at the this typical integration scheme in the microfabrication roads, that typically from the front end to the back end. To introduce chemical sensors, we can look at we can have a film deposition. Then we can use lithography to have the pattern of the typical materials on the surface. And we can do etching to have the pattern. Then we can also do doping to tune the properties of the materials. So after engineering on the front end, then we can dicing the device, and from packing we can have the devices. So from this scheme, we can see that the key point to introduce MOF materials into electronics is the thin film deposition and patterning. So these fabrication roads are the key and starting point for microelectronic integration. So then the question comes to us, so how can we do MOF thin film deposition and patterning? So we look at typical MOF synthesis. So we need to introduce, for example, the MOF materials on the surface. And typically, if we work with MOF material, mostly we use solver thermal or hydrothermal synthesis, this solution-based synthesis route. So typically, we can have the bulk powder materials. So it is kind of difficult to introduce this kind of bulk MOF powders on the surface on the electrical devices. So what should we do? So we need to have defect-free layer and coatings, and we need to do surface patterns and also control the crystallographic orientation. And we also need to study the compatibility with other functional components, for example, electrodes or other materials on the electronics. So we need to study the integration compatibility. So today I'm going to talk about two of my work on the first two topics. First is thin film deposition. So we first aim to develop a technique to deposit defect-free layers or coatings. So first technique we were thinking about is a layer-by-layer growth, because we know MOFs are constructed by a metal part and an organic linker part. So we developed a method called layer-by-layer growth. So it's kind of a simple method. So we first functionize the substrate, for example, have the silicon or glass to have the self-assembly monolayer on the surface. Then we alternatively immerse into the metal solution or the linker solution. Then we use solvent to rinse the unreacted component. Then by repeating this repeating this procedure for many times, we can have the MOF film on the surface. So by using this method, we can have a smooth morphology, and we can control the thickness by control the deposition cycles, and even we can control the crystallographic orientation. Taking one example, for instance, here we have copper NDC double, so it is a kind of pillar layer structure. It has a copper paddle wear and connected by this naphthalene dicarboxylate to have the shield-like sheet. Then we have the double molecules to pillar this sheet, and we can have a 3D porous structure. And when we using layer by layer deposition, so using copper acetate and the NDC and double solution to deposit this kind of MOFs on the surface, for example, in predetermined SAM, then we can see the growth in this 001 orientation. So if we look at the structure, so it goes along this direction because of the pyridine can bind this copper, the copper acetate in this way, then it can grow along this direction. But if we functionalize the surface with carboxylate, then it can grow in this orientation. So we can, from the outer plane XID, we can only see this reflection. So which demonstrates a perfectly oriented film. By using this method, we can not only deposit single layer MOF film, we can also work with heteroepitaxial growth or MOF thin films. Basically, we can introduce two different MOF films on one surface, and both of them are grown oriented. So, for instance, here we have copper NDC double on the bottom, which is tetragonal structure, and the metal side is copper acetate, and the linker is NDC and double. And the top layer is copper BTC, so it is from copper acetate and the benzene triocarboxylate. It's also called HCAS1. So both of the MOF system shares the same copper center, but the linker are different, and also the structure are completely different. So by using the layer by layer method, we can first have MOF A in the bottom, and we can continue the growth of MOF B, copper BTC, and we can have both of the layer on the surface. So here we can see by the in situ post-crystal microbalance characterization. So if we look at the black one is the first layer deposition, we can see the layer by layer. So it is a gravimetric measurement, so we can measure the mass change on the surface. So we can see the layer by layer feature of the first layer and the layer by layer of the second layer. And if we look at the interface, so in the last cycle of copper NDC double, we can copper acetate, then NDC double. Then we deposit copper acetate, and we have BTC linker. So then to connect the bottom layer, and if you look at the outer plane XRD, you can see from the bottom layer it grows in the OO orientation. Then for the copper BTC, it also shows oriented growth in the 111 orientation. So so this kind of technique is kind of straightforward. It's simple, and it has its advantages. But the only problem of this kind of method is to work with big areas. So typically we work with 1 inch or 2 inch, then we can get kind of homogeneous film. But if we work with large area, typically if we want to use in the clean room fabrication, then we need, for example, 4 inch or 8 inch wafer. Then this method is difficult to get homogeneous MOF films. So then the group, Rob Amelov's group, developed a vapor phase deposition, so-called MOF CVD. So it is kind of two-step vapor phase deposition technique. So the first step is to deposit the metal oxide as a precursor layer. Then we use organic linker, the vapor phase, so the vapor phase linker to react with the precursor layer to get the MOF film. So let me introduce a bit into detail. The first step they use atomic layer deposition. So atomic layer deposition is kind of similar like what I discussed before, the liquid phase layer by layer deposition. So here is kind of gas phase layer by layer deposition. So first you have diethyl zinc deposited on the surface. Then you have purge cycle to remove unreacted precursor. Then you have water to react with diethyl zinc to get ether out. Then by repeating this procedure for many times, you can have different thickness of zinc oxide. And the growth per cycle is 1 angstrom. So this kind of method can tune the size very precisely in angstrom level. And then the next step is to have vapor solid reaction. So we do the deposition at a little bit higher temperature, is around 110, 120, to have the linker here in this case is 2-methylimidazole. you can sublimer, and you have the linker, vapor phase linker to react with the zinc oxide, and to neutralize, and you have the water out. Then by continuous growth, the linker can penetrate into the MOF film and reach the bottom of the zinc oxide. Then you can have the ZIF8 film. Then it has very homogeneous and porous structure. And you can see from the scheme, you can see typically zinc oxide, it has higher density. When converted to the porous structure, the density is getting lower, and you can see the thickness expansion. So we can get the MOF, different MOF films, different thickness of the MOF film by tuning the thickness of precursor layer. So the key advantage of this method is conformal and wafer scale deposition. The conformal deposition means so it can grow not only on, for example, flat surface, and also can deposit on this high aspect ratio. Here, for instance, here we have the aspect ratio of 25 to 1. And if you can see the pillar, this is the silicon pillar. Then we can do the MOF film both on the, we can do all the area. So also the top and also the bottom, you can see the MOF growth on these pillars. And another advantage is the wafer scale deposition. So they demonstrated the deposition on the 8-inch silicon wafer. And by measuring 100-point ellipsometry, you can see the homogeneous MOF film coating on this big scale wafer. And this is a demonstration of ZIF8, one typical MOF. So then when we want introduce this MOF into introduce this technique to other MOFs, we meet a problem, so-called polymorphism issue. So taking one example, here we have zinc oxide. When we want to deposit, react with dichloroimidazole, and we expect to have this so-called ZIF71. It's a row topology, and it has highly porous structure, and the pore size is bigger than ZIF8. This is what we expect. But when we do the reaction, we get this ZIF72. It is a non-porous dense structure. So then we ask ourselves what the reason behind. So why we can, for ZIF8, we can get the porous structure, but for this kind of linker, we cannot get the porous structure. Instead, we get the dense structure. And we go to the synchrotron to do this in situ XRD measurements. So we can just by kind of in situ measurement of the zinc oxide and the dichloroimidazole reaction, monitor the reaction. So we can see at very beginning, we can see the formation of ZIF71, which you can see these these reflections, which belongs to ZIF71. This is porous structure. But with the reaction, we can see the disappearance of ZIF71 and the formation of the other MOF. Actually, this is MOF72. It's this dense structure. And if we integrate this the peak, then we can see the reaction profile here. So firstly, we form ZIF71, and it disappeared. Then we formed ZIF72. So we propose that ZIF71, this porous structure, is kinetically preferred, and this ZIF72 is thermodynamically stable. So within this reaction going on, so the ZIF71 can conform to ZIF72. Then we perform another measurement to confirm our hypothesis. So we first have a ZIF71 by solver thermosynthesis. Then we react with this linker. So we didn't do any other reaction. So we just place ZIF71 and this linker together at relatively low temperature, 130. Then we can see within a few hours, this ZIF71 converted to ZIF72, which also confirms that ZIF71 is the kinetically preferred, but ZIF72 is thermodynamically stable phase. So the question comes to us: how can we get the ZIF71 we wanted? So we come up to an idea to have template-mediated control over this polymorphism. So during this chemical vapor deposition, we have zinc oxide reacted with dichloroimidazole vapor, and we introduce, for instance, DMF or ethanol vapor, we get this porous structure. But when we introduce water vapor or we didn't add any additive, so we get this ZIF72, this dense phase. So here I just show you one example. When we use DMF as a template, we convert 5 nanometer zinc oxide from the gradient incidence XRD. We can see that the ZIF71, we can get ZIF71 film, and the film is kind of smooth by AFM measurement and the SEM measurement. Then we see we can also control the thickness. So the thickness made by epsometry and the roughness made by AFM. So we calculate the theoretical expansion factor is around 20. So if, for instance, we have 5 nanometer zinc oxide, we expect to get 100 nanometer ZIF71. So the black one corresponds to the film thickness. So we can see we can have a good control of the MOF film thickness, and the roughness, well, it's not too high, but within the increase of the MOF film thickness, we can see the roughness is also going higher. So then we come to the question, how what's the reason behind? So we also made the synchrotron in situ XRD. So we see from the when we use water as additional additive, we can see so water cannot avoid this phase transition. So it first forms ZIF71, then it slowly disappeared, and ZIF72 formed. And when we use DMF and ethanol, we can see ZIF71 quickly formed, and ZIF72, where it start to form, are very slow. So in this case, around 45 minutes. But if without any additive, so it quickly transformed to ZIF72. We can see at 120 degrees C, it prefers to form ZIF71, but we cannot completely prohibit this phase transition. Then we lower the temperature to avoid this phase transition. Then we work, for example, with DMF at 105 and ethanol with 90. We didn't see any formation of ZIF72, and we can get a phase pure ZIF71 MOF film. Yeah, this is the first case on the MOF CVD deposition of the MOF film with template in this case. And the second topic, I'm gonna talk about my recent work on this surface patterning with MOFs. So first, I'm gonna introduce a bit about photolithography. If you are not very familiar with photolithography, I'm gonna quickly introduce a bit. So photolithography is a conventional technique that you have film patterning on the surface. Typically, you have the film you want to deposit, you want patterning, then you have coating of the photoresist on the surface. Then by exposure of UV light and covered by a photo mask, then the UV light can go through this photoresist to induce chemical changes, then have solubility change. So by immerse into the the photoresist into a developer, then you can remove this, either remove the UV light irradiated area or the unexposed area. So you can have positive pattern and the negative pattern. So after etching and remove the photoresist, you can have the pattern of the surface of the film you want. But when we use MOF film for this photolithography for MOF film patterning, we have the problems of first resist contamination. We know MOFs are highly porous structure, so the component of the photoresist can penetrate into the MOF film and contaminate the MOF film. And also we know most of the MOFs are basic sensitive or acid sensitive. So when we use the developer, basically is a basic solution, you can damage the MOF, or the strap for negative resist is acidic solution, can also damage the MOF film. So it has, this conventional photolithography has problems for MOF patterning. So then I come up to an idea. So is it possible to direct pattern the MOFs? So we consider the MOFs as a photoresist. Then after some light exposure, we can just easily get the MOF patterning without any other resist. So for using these MOFs as kind of resist, the key is the solubility switch after light exposure. So it means, when we irradiate any light, so it introduces some chemical changes on the MOFs, then so you introduce some solubility switch, then we can do the MOF patterning. So within this idea, we brought a lot of MOF to the synchrotron. We come up to the idea of X-ray, because typically MOF are stable in the typical, for example, UV light, but we think X-ray is a strong high energy light, so it can damage some of the MOF. Then we can introduce some chemical, some solubility changes. So we found one the typical types of MOFs are very interesting. So these halogenated MOFs. So taking one example is, again, dichloroimidazole, and we found a very interesting properties. So when we irradiate this kind of MOF with X-ray, so we first see the crystallinity, the loss of the crystallinity. So with irradiation, we see the loss of the crystallinity. And one very interesting property is, so we see after irradiation of LIF71, we found this MOF is soluble in DMSO and partially soluble, for example, in ethanol, acetone, or water. But the MOF itself is not soluble in any of these typical solvents. And we also found other LIFs. So for example, benzene imidazole or methyimidazole, this kind of MOFs with this linker, after irradiation, they are not soluble in DMSO. So this is very exciting news for us, because we see the X-ray can induce damage of this MOF, and it can be soluble in DMSO. So what does it mean? So it means we can do X-ray lithography on this MOF film. So basically, it's kind of very straightforward. We have a LIF71 MOF film, and we covered it with X-ray mask. So the X-ray can selectively penetrate and going through the MOF film. Then after the development, we can have the MOF pattern. So here just show some characterizations. Here we have grazing incidence Sachs measurement. So we can see after the patterning, we can also see the structure doesn't change. And from the optical profilometry, we can see the high quality of the MOF patterning. You see the periodical structure, and also from the FM and SEM measurement, we can see the exposed area being completely removed. So it's a kind of clean patterning. And not only by patterning these MOF thin films, because of the high energy of X-ray, it has a very high penetration depth. So it can also do the patterning for thick film. And also here for one demonstration, we can do the patterning of single crystal. So we have instance MOF single crystals on the surface, then we covered it by the mask. And after development, we can ship the single crystal. And here is the pristine single crystals. And here we can see a kind of a knife cut on the crystal. And we can see here is some rod, but unfortunately it doesn't stand on the surface, but it kind of collapses on the surface. And we can also make some holes on some of these periodical holes on the MOF crystals. And a very interesting property is when we bring these single crystals to do single crystal XRD measurement, we can also solve the structure. So it still remains the single crystalline property. We didn't have any damage on this unexposed area. And then we did some mechanistic study of these X-ray induced changes. The first idea is to do NMR measurement. So we have this dichloroimidazole. We see it has only one proton here. It is around 7.7 something. After X-ray exposure, we see many peaks, which makes us very difficult to resolve which component we have after the X-ray exposure. But one point we are very certain, we are very sure is we have many different products. So this linker is being damaged, and maybe there's many other reactions involved. So it has many different products in the system after X-ray exposure. Then we also did some elemental analysis. So if you remember before, we mentioned like after X-ray exposure, these MOF are partially soluble in water. And so we did elemental analysis on water soluble part. It has zinc, all the these three elements. And interestingly, for the water insoluble part, it doesn't have any zinc, so it has a lot of carbon. So we propose after X-ray exposure, it has like oligomer or polymers, which is not soluble in water but soluble in DMSO. And the water soluble part, it may have some zinc nitrogen coordination complex. And we also did some XPS analysis. So if you look at here for chlorine, then the Princeton one, it only has carbon chloride, carbon chlorine. Then within the increase of the X-ray exposure, we see a lot of zinc chloride formation, so which support our hypothesis. So the X-ray induce the formation of chloride radical, and it cleaves the imidazole ring and induce other reactions. Also, it forms zinc chloride, and also it cleaves the zinc nitrogen bond. So this is what we understand so far for this kind of mechanics study, but still we cannot resolve all the reactions in this complicated system. And within the after the X-ray reduction, sorry
to interrupt. Just to mark this. Let's say 10 minutes more for your final explanation and also some questions. So you can.
Okay. Yeah. So so X-ray lithography is kind of, you use a mask to do this lithography, and the resolution where it's kind of high, you can reach like sub-micron level. But with the mechanics study, it has this electron-induced some changes. So we can also use this patterning by electron beam lithography. So we typically, it's kind of the same. You have morphium, but here we don't use any mask. We have an electron beam to write on the surface. Then after the development, we have the morph pattern. So we immerse this after irradiation. We immerse this sample into DMSO and to remove this exposed area, then to have morph pattern. And here is our e-beam tool. And we can see the 50 nanometer trenches. It's kind of a knife cut on the surface. Then we have the periodical patterns, and we can also have these lines. And we also achieved a very high resolution patterning by e-beam lithography. And here shows some examples with this grid. We can achieve 50 nanometer, 60 nanometer grid, and also even 30 nanometer grid, where it is not very regular because it has also some proximity effects and some forward scattering and back scattering induce some not very uniform, but you can still see it's kind of periodical structure. And another advantage of e-beam lithography compared with some mask-based lithography is it has a freedom of writing. So it basically can write any kind of 2D pattern you want. So here we show you some circles, and I show you some text and other shapes. So shapes based on what you want. And so by this, so we demonstrate this high quality of the patterning by by X-ray and E-beam. And another question comes to us. So we know MOFs are porous materials. So after patterning, whether or not it can still maintain this high porosity. So we did some porosity analysis before and after the measurement. So if you remember, before we can do the MOF coating on these high aspect ratio pillars, so we can have a lot of highly large area on the flat surface. So for example, you have the surface on the pillar depth on the surface. If we have 1 square centimeter, we have more samples on the surface, then we can do the volumetric krypton absorption. So if you look at the red one, is a MOF film coated on these pillars, then it shows this type 1 absorption isotherm. And based on the krypton absorption isotherm, we calculate the film surface area is around 250 square meter, but here we don't know the mass of our MOF film. We only know the area of our MOF film, so we have the unit of square meter per square meter. So after the patterning, you see here we can selectively remove certain parts of the MOF film. Then you see this is kind of very clean, and this is our MOF film. We calculate again, we did the Krypton sorption again and did the calculation for the MOF pattern. We have around 236 square meter per square meter. So we can confirm that the porosity remained, maybe very slight changes. And also we can also do this methanol adsorption on this quartz crystal microbalances, kind of gravimetric measurements. So we have more film coated on the surface and introduce methanol and monitor the frequency change and to calculate to the mass change. Then before and after the patterning, we made the methanol uptake, so we can see kind of similar adsorption isosome, both the shape and the quantity. So with both of these measurements, we can confirm after the X-ray or E-beam lithography, we can remain our porosity. And with this patterning, we did some demo of our potent MOF film, use it as a photonic sensor. So we have this MOF patterning periodic structure. Then when we irradiate the film with a red laser, with visible light, the laser, so kind of a single crystal diffraction, but here we use visible light instead of X-ray. So we have visible light irradiated to the periodic structure, then we have the diffraction spot you see here. And according to this equation, so the first order intensity, diffraction intensity is related to the phase change, and the phase change is related to the refractive index change of the pattern. And so if we have gas molecules into our MOF pores, then the refractive index is changed, then is introduced to the then we can see the first order diffraction intensity will be also changed. So by using this scheme, we can do the gas sensing. So we develop a very simple sensing test system. So we have light laser shining on our MOF pattern. Then we can see the diffraction spots. Then we, by monitoring the intensity change of the diffraction spots, then we can realize the sensing signal transduce. And here just show you one example of the methanol vapor sensing. So we can see this kind of, well, it's not completely reversible sensing, and the response around 1 minute. And we can, so the red one is a refractive index we made by ellipsometry, and the blue one is the intensity, relative intensity change of the first order diffraction spot, and it shows kind of very similar shape. And also this also confirms that the porosity of the MOF film after patterning then changed. So come up to the summary. So we consider that first on the part of the MOF film deposition, we developed a template-mediated CVD process to control the polymorphism, and also we also use this in situ synchrotron sacks to help us to understand the phase transition during the CVD process. And we also developed a direct patterning of MOFs without the use of photoresist by X-ray and E-beam lithography, and we also achieve this sub 50 nanometer resolution and use it as a chemical sensor. And finally, I would like to, this is kind of collaborative work, and I would like to thank my postdoc mentor in K Leuven in Belgium, Rob Amelot, and our clean room managers, and also our collaborator in Professor Fischer in Munich, and our collaborator in the ultra synchrotron trace in Italy for X-ray lithography and the in situ sax measurement, and our collaborator, Professor Paulo Faccaro in Graz in Austria. And also I would like to thank my funding. Without this funding, we cannot do this kind of experiments. First, the ERC funding, and also my Marie Curie fellowship and the NFFA to support us to do this synchrotron measurement. And thank you very much for your for listening. And I'm very happy to answer any questions. Thank you very much.
Thanks, Min. It was an excellent presentation and a lot of interesting ideas, and I'm sure all the audience is very pleased and they have a lot of questions. But unfortunately, we have time for a few, maybe one or two. There is a question from the audience. Juan Alegreto from Argentina likes to congratulate you on your talk and your work. And the question is, in order to grow two MOFs in an heteropitaxial fashion, is there any parameter other than crystalline cell lattice to look at to sort of predict if the structure would be viable or not?
That's indeed a good question. For us, is when I work with this let's say these systems, the key point is for these two MOFs, even though they are completely different structure, but they share the same. They have the same the metal center. It has the same copper paddle wheel unit. So that's the key point. Then we can continue the growth. And another interesting thing is the top surface of the bottom layer is also important. So if you see here, if for example, and make it to for screen. So if we have the MOF here, we have, if we grow in this direction, then we have the top layer, we have copper paddle wheel. Then we can continue our growth with BTC. Copper paddle wheel can coordinate with BTC. But if we introduce other MOFs without not in this system, well, it might be possible, but I'm not very sure. It's kind of difficult. So it's kind of based on the surface chemistry of the bottom layer, which kind of has a template effect for the second layer growth. This is my understanding.
Yeah. Okay. Perfect. And maybe one more. Germán Gomez want to thank you for your talk also. And he wants to ask if you could mention about the mechanical properties of the anchored thermos in view of a potential device application. And if according to your expertise,
that's indeed a really good question. Indeed. So if we want to introduce this MOF material, for instance, into for instance into this kind of devices, the mechanical stability is kind of very important. Unfortunately, I didn't do any research on this point. So I'm mostly working on this fabrication route. From the intrinsic properties, I think as far as I remember, there are some groups in UK, in Oxford and Cambridge, Thomas Bennett and Jin Chung in Cambridge, and Professor Jin Chung Tan in Oxford. They did kind of not really comprehensive, but they did a lot of study on this point. But unfortunately, I didn't do any research on this point.
Yeah. Okay. Okay. Well, it's interesting, and then you mentioned those reference for our colleague to look at. So I think we are in time for our next speaker. So again, I would like to thank you, Min, for joining us, and let's keep in touch, and then we can share ideas and
Yes.
look at future endeavors together. So thanks a lot for coming, and congratulations again for your hard work.
Thank you. Yeah.
Thank you very much.
So bye. Yeah.
Bye, Min.
I would stop sharing and for the
correct.
next speaker.
Great.
Okay.
Great. So our next speaker, I will introduce nuestro próximo, como es de España, podemos presentar en español y hacer alguna pequeña referencia en inglés. Así que bueno,